So projectiles, inclined plane, type 3, horizontal landing. So this example comes from Rowntree, and we can see here that we're given a particle is projected upwards with the speed of 35 meters per second from a point O on a plane that is inclined at an angle of 45 degrees to the horizontal. And it's projected upwards. So the angle of projection is theta, and it's with respect to the inclined plane, so it's not with respect to the horizontal. And we're told that if the particle is moving horizontally when landing, that we have to show that cos theta is equal to 3. Okay, so let's draw a diagram to see what is happening here. So we have our inclined plane, and that has an angle of 45 degrees. And then we have the particle is projected up into the air, but it lands horizontally. And therefore we know from our geometry that if we have two parallel lines and a transversal cutting those two parallel lines, then we have alternate angles. So in other words, the landing angle must be equal to 45 degrees. So that's going to be key to our solution. But we also know that on landing, Sy is equal to 0, which will allow us to work out our time of flight. Now, the other information given to us is that it's projected with a speed of 35 meters per second, and that the angle it makes with respect to the inclined plane, in other words, the angle of projection with respect to the inclined plane, is theta. So what we want to do now is we want to write out our table for U, A, V, S and T. So I'm going to get you to pause the video and you're going to complete the table. Okay, so we know that our initial velocity, if we break it down into our I and our j components, is U cos alpha I plus U sine alpha j. And another thing to note then is we have 45 degrees here. So if we have cos 45, that's going to be 1 over root 2. And if I have sine 45, that's also 1 over root 2. So that will come in handy at any point that arises in the question. Okay, so in the I direction or the x direction, then we say U cos alpha. Well, what's our alpha? Our alpha is theta and our beta is 45 degrees. So that's just going to be U cos theta. And in the y direction, it's U sine theta. A is our gravity, and we have to remember that with gravity, it's going to be minus g sine beta in the x direction. So that's minus g over root 2. And in the y direction, it's minus g cos beta. So that's going to be minus g over root 2, because our beta is our 45 degrees. Okay. And if we're looking at V then, well, V is equal to U plus AT. So V in the x direction is equal to U cos theta minus G over root 2t. And V in the y direction is U sine theta minus G over root 2t. S, we have to remember, is ut plus a half at squared. And therefore S in the x direction is U cos theta t minus G over 2 root 2 t squared. So in other words, half at squared. S in the y direction is U sine theta minus G over 2 root 2 t squared. So again, another half at squared. Okay, and remembering obviously the reason your gravity is negative is because obviously gravity is always acting in a downward direction to the inclined plane. So if we're resolving that in the y direction, well, originally it was projected up the plane. So therefore your y is now in the opposite direction and your x is also in the opposite direction. So this is why we have negative signs, and therefore this is your opposite side to the angle and your adjacent side. So therefore your adjacent or your y is your cos and your opposite is your sine. Okay. All right, so how are we going to use this table? Well, we know that our information is when it is landing, that sy is equal to 0, and that's going to allow us to work out our time of flight. So what was sy? Well, we said sy was u sine theta t minus g over 2 root 2 t squared. And if I let that equal to 0, then I can isolate t by taking out the highest common factor. I'm going to multiply across by 2 root 2 first of all though, just to eliminate any fractions. Get rid of the mess. And take out t as being common, so we have 2 root 2u sine theta minus gt. So both of those factors multiply to give us 0, which means that one or both must be equal to 0. So that gives us t is equal to 0, or 2 root 2u sine theta minus gt is equal to 0. In other words, t is equal to 2 root 2 u sine theta all over g. Now, I've just realised obviously that I haven't put in my u there. U is 35 metres per second. So realistically, I should actually have 35 in that table all the way down. I haven't put it into the table now, I apologise. But that doesn't matter because at this point now we can say, but u is equal to 35. Just in case you thought you had your table filled out wrong, you didn't. You had it filled out right. I'm the one who has done it without the 35. Okay. So now I can stick in my u, and if I multiply 35 by 2, I get 70 root 2 sine theta over g. And why are we getting 2 times the flight? Well, the only times when sy is 0 is at the start, so the displacement above the inclined plane is 0 at the start, and also at the end. So it's landing at the same position above the ground at the start and at the end. So basically t is equal to 0 at the start and t is equal to 70 root 2 sine theta over g at the end, which we call our time of flight. Okay, so what we now can look at is the fact that we have our second piece of information, which is our landing angle. And we saw that the landing angle L is equal to 45 degrees. But of course, what is the landing angle? Well, tan L is equal to minus Vy over Vx. So you can work out your Vy and your Vx separately by putting in your time of flight, or you can sub in our values for Vy and Vx and L here and rearrange to get t in its own, and then equate your 2 time of flights. That's up to you how you work with it. What I'm going to do is I'm going to get the 2 times of flights and equate them. So again, it's all personal choice, but both would give you the same answer. So you either sub in your time of flight now and then try and get your cot theta equals 3 out, or you try and get your time of flight and then equate them. Okay, so the reason I'm going to work with subbing in for L and then getting t on its own is because I know tan 45 is going to give me 1, so I know that's really nice and simple. So therefore minus Vy, well, Vy we saw was u sine theta minus g over root 2. So I sub in there. So it's u sine theta minus gt over root 2. And that's over Vx. Vx is u cos theta minus gt over root 2. And of course you can see here I can put in my 35 in a second as well, okay? So tan 45 is 1. U is equal to 35 meters per second. But you'll have that already in there. Okay, so therefore that's minus 35 sine theta plus gt over root 2, and that's all over 35 cos theta minus gt over root 2. So I'm going to cross multiply there. So I get 35 cos theta minus gt over root 2 is equal to minus 35 sine theta plus g over t root 2. So I'm going to bring all my t's to the left hand side. So therefore that gives me 35, sorry, it gives me 2 gt over root 2 is equal to 35 cos theta plus 35 sine theta. So I've brought everything to the left and the t's to the right, and then left to right is equal, okay? I'm going to take out my t on its own then, so I'm going to multiply across by root 2 and take out 35 as being common there as well. So 35 multiply across by root 2, divide across by 2g, and I've taken out my 35 as being common there, just to make it a little bit neater looking. Okay, so this is also my time of flight. So I now have two equations for my times of flight, so I'm going to equate both of those. And if I equate both of those, what do I have? Well, my first one was 70 root 2 over g sine theta. My second one is 35 root 2 over 2g cos theta plus sine theta. So equating, I have 70 root 2 over g sine theta is equal to 35 root 2 over 2g, and that's times cos theta plus sine theta. Well, I can see what's going to cancel. Well, 35 will go into 70 twice. Root 2 will go into root 2. G will go into g. Okay, so that leaves me with 2 sine theta on the left is equal to cos theta plus sine theta all over 2. So multiplying across both sides by 2 gives me 4 sine theta is equal to cos theta plus sine theta. And then if I bring over the sines to the left, well, that gives me 3 sine theta is equal to cos theta. Oh, we're getting excited now because we've got a 3. If I divide both sides across by sine theta, then I get 3 is equal to cos theta over sine theta. And in the video you would have seen that that means what? Well, it means tan, doesn't it? But it's tan upside down. So page 13 of your maths tables, what do we know? We know that tan theta is equal to sine theta over cos theta, and therefore tan theta is equal to 1 over cot theta. So therefore if I invert my cos over my sine, well, that basically means that cot theta equals 1 over tan theta, and 1 over tan theta is cos theta over sine theta. And what do we have? We have cos theta over sine theta. So that's pretty cool, because that means then that cot theta equals 3.